Welcome to the world of advanced Bash scripting. In this video, we will dive into powerful techniques and best practices that will elevate your shell scripting skills to a mastery level. We will explore how to write more efficient, robust, and maintainable scripts. Bash scripting is an essential skill for any Linux user or system administrator, and mastering it can greatly enhance your ability to automate tasks and manage systems effectively. We'll cover function libraries, modular design, advanced process management, robust error handling, and testing frameworks. Functions in Bash provide powerful ways to organize code. We can return values using exit codes, pass arguments with named parameters, create function libraries for reusability, and use local variables to prevent namespace pollution. Look at this example. We define a function called validateInput. Inside the function, a local variable input value is assigned the value of the first argument passed to the function. This ensures that the variable's scope is limited to the function, avoiding conflicts with variables outside the function. The code checks if the input value is empty. If it is, the function returns 1, indicating failure. Otherwise, it returns 0, indicating success. Creating function libraries allows you to reuse code across multiple scripts. In this example, we have two files. The first file, utils.sh, contains a library of functions. It includes functions for string manipulation such as to uppercase and validation functions such as isNumber. The second file, main.sh, sources the utils.sh file using the source command. This makes the functions defined in utils.sh available for use in main.sh. The script then calls the isNumber function to validate an input and converts the input to uppercase using the toUppercase function if it is not a number. Defensive programming techniques ensure your scripts fail gracefully. Setting error handling flags at the script start, checking command exit codes consistently, and creating custom error handlers are essential. Let's look at the example. The set command with the options -e, -u, and -o pipe fail ensures that the script exits immediately if a command fails, if an undefined variable is used, or if a command in a pipeline fails. A custom error handler function is defined to print an error message and exit. The trap command is used to call the error handler function whenever an error occurs. Advanced parameter handling techniques include parameter expansion for default values, length checking, and substring operations. Using the getOps command for option parsing allows you to process command line options with short flags, like -a or -b, in a standardized way. You can also implement named parameters for more readable function calls. Look at the example. The name variable is assigned a default value of anonymous if no argument is provided. The output directory variable is assigned the value of the second argument, and the script exits if it is not provided. The getOps command is used to process command line options, such as -f for filename and -v for verbose. Process management and job control involve running processes in the background and managing their execution. The diagram illustrates a main script executing processes in parallel, with the wait command ensuring that all background jobs are completed before the script exits. Let's understand with the code. The process file function simulates processing a file by printing a message, sleeping for 2 seconds, and then printing another message. The script launches multiple instances of the process file function in parallel, using a for loop and the ampersand symbol. The wait command is used to wait for all background jobs to complete. Effective debugging techniques are crucial for identifying and fixing issues in your scripts. The trace mode, enabled by set-x, prints each command before execution, allowing you to follow the script's flow. Verbose output involves adding debug flags to show detailed information. PS4 customization allows you to customize trace output with line numbers and timing. In the example, set-x enables debugging for the entire script. The PS4 variable is customized to include the source file and line number in the debug output. The debug section function demonstrates how to enable and disable debugging for specific code sections. Testing is crucial for ensuring the reliability of your scripts. Isolate functions for unit testing. Create test fixtures and mocks. Use frameworks like BATS or SHUnit 2. Integrate with CI/CD pipelines. Test edge cases and error conditions. Let's see this example. This code shows an example test suite using BATS. The first test is number validates numeric input. Checks if the isNumber function correctly validates numeric input. The second test, to uppercase convert string, checks if the to uppercase function correctly converts a string to uppercase. Optimizing performance ensures your scripts run efficiently. Use native bash commands instead of external processes to reduce overhead. Minimize subshells by avoiding unnecessary command substitutions and process spawning. Process data efficiently by using stream processing with awk or set instead of loops for large datasets. Inefficient code example shows a slow way to iterate through a sequence of numbers using a subshell. The optimized code example shows a faster way to achieve the same result using bash built-in sequence expansion. Following best practices ensures your scripts are maintainable, secure, and reliable. Document your scripts with clear headers, usage examples, and function descriptions. Validate all inputs, avoid eval, and quote variables to prevent injection attacks. Break scripts into reusable functions and libraries, keeping functions focused on a single task. Design scripts to be safely run multiple times without causing unintended side effects, ensuring idempotency. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.